Hey guys, it's Miss Manili, and I'm going to go ahead and go through the probability review with you. It's really important that you guys understand how to interpret the problems and then have a good strategy for solving them. And we're going to use a variety of methods to answer questions in this review. So for example, you're going to be using simulations, the probability rules, Venn diagrams, two-way tables, and tree diagrams. Many of these problems can be solved in different ways, but some of them, there really is only, there's one strategy that'll be the best strategy to use. So I'm going to try to show you all of the different alternatives and at the same time kind of reinforce the best strategy for solving each type of problem. All right, number one, and I think they kind of go in the order that we learn them. So number one, it says, suppose the probability that a U.S. resident has traveled to Canada is 18%, to Mexico is 9%, and to both countries is 4%. What's the probability that an American chosen at random, and then you've got three different scenarios. So in this case, because traveling to Mexico and traveling to Canada, I'm not looking at a sequence of events. I'm not looking at like first they're going to Canada and then they're going to Mexico. It's just two very similar events that overlap because we are given the probability of visiting both countries. So in this scenario, it's going to be best to construct either a Venn diagram or a two-way table. And either one is the same. Like the Venn diagram and the two-way table express the same probability. So whichever you're more comfortable with. I like to do a Venn diagram just because I like to draw pictures. I think it just helps illustrate oops, the sample space a little bit better. So remember, your sample space should be contained, so it's finite. And then I have two different outcomes here. We have going to Mexico, and I'm just going to call that M, and then we have going to Canada. And I'm going to refer to that as a C. Now be careful in this problem because it says that 18% of residents have traveled to Canada. I have to be careful because that means that 18% are going to be in this big circle of Canada. So if I also have people that have gone to both countries, and I know 4% have gone to both countries, then I'm going to need to put my 4% in between. And I'm sorry, my board isn't calibrated, so let me pause this and fix that. Okay, so where was I? So I know 18% of residents have traveled to Canada. So that's this whole circle. I know that 4% have traveled to both countries. So it's always a good idea when you're doing your Venn diagram to go ahead and put the overlap first. So the probability that they visited both countries is 4%. When I'm going to figure out the rest of my Canada circle, I need to now subtract that 4% from the 18%, and that leaves me with 14% visiting just Canada. If I want to figure out the percentage that have visited just Mexico and not Canada, I have to take what I know about Mexico, which is that 9% of Americans have traveled to Mexico, and I have to subtract that 4% overlap. That means that 5% have visited just Mexico. If I want to figure out the percentage that haven't visited either, then I need to add up my probabilities. So that's going to be 5, 9, and then 23% have visited either Canada or Mexico. If I subtract that from 1, that means that 77% have visited neither. And again, you can set this up as a two-way table. Your probabilities are going to be the same. In letter A, it says travel to Canada, but not Mexico. Remember, on the test, you will have to write the probability statement for each problem. And if you want to write it out as the probability of Canada, but not Mexico, because you're afraid that you're going to get the notation wrong, that's totally fine. I'm going to write it using symbols. So I'm letting C represent Canada, and it's probably a good idea for me to go ahead and define my events. But if I want to do Canada but not Mexico, but is another way of saying and, so that would be Canada and not Mexico. And there are lots of different symbols that you can use for not. So if I'm looking at Canada and not Mexico, I'm looking for, go ahead and get a highlighter here. So if I'm looking for everything that overlaps Canada and not Mexico. So here is my Canada, and change the pen color. If I want to look at not Mexico, and I'm going to color in everything that is not in Mexico. And since it's an and, I'm looking for the overlap. And the overlap occurs right here. And that, I know, is going to be 14%. And you can look right at the Venn diagram and tell that. Traveled to either Canada or Mexico, that's going to be the probability of Canada or Mexico. Remember, with an or, that is a union, so I'm basically looking at everything that is within my circles here. So that's going to be 0.05 plus 0.04 plus 0.14, and that's going to be 23%. Not traveled to either country, that would be the probability of not, and I can write it this way, Canada or Mexico. Or I can write it as the probability of not Canada and not Mexico. But either way, I'm looking at this 77% of the population that hasn't visited either. And you can also do this as just 1 minus 0.23, which is the probability of visiting Canada or Mexico, because it's just the complement. In letter B, you could also use your probability rule. Remember, if we are looking for the probability of A or B, in this case we're looking at C or M, that's going to be the probability of C plus the probability of M minus the probability of both. Now be very careful. If you're using the rule, then you don't want to refer to your Venn diagram. You want to refer back to the problem itself. The probability of visiting Canada we were given as 18%. The probability of visiting Mexico we were given as 9%, and the probability of both we were told is 4%. So if you want to use the rule, that's fine, but don't combine it with the Venn diagram. And if you do this, you'll again get 23%. Okay. In number 2, it says, in its monthly report, the local animal shelter states that it currently has 24 dogs and 18 cats available for adoption. 8 of the dogs and 6 of the cats are male. If an animal is selected at random, what is the probability? And then we've got male, what's the probability that it's male given it's a cat, and so forth. In this case, because we're looking at dogs and cats and males and females, it might be a little confusing to try to do this in a Venn diagram. In this case, because I'm categorizing the animals 2 different ways, by the type of animal and by their gender, a two-way table is probably going to make the most sense here. So if I have male versus female and dog versus cat, it might help me set up this problem a little bit better. So for example, I know that there are 24 dogs in the shelter. So I know the total of the dogs is 24. I also know that there are 18 cats available for adoption. So that gives me 42 animals total. I know that 8 of the dogs and 6 of the cats are male. So 8 of the dogs and 6 of the cats are male. That'll help me figure out the number of female dogs and cats. So since I have 24 dogs total, that means I must have 16 female dogs. And since I have 18 cats total, I must have 12 female cats. And if you want, you can go ahead and find the sum of your columns as well. So this would be 28. And now I've got a two-way table because I've categorized these animals 2 different ways. So I'm trying to find the probability that the pet is male given that it is a cat. So as soon as you see the word given, that's a dead giveaway that you're dealing with a conditional probability here. I'm trying to find the probability that it's male. The given information always comes second. So in this problem, since I'm trying to find the probability of the animal being male, but I already know that it's a cat, that means I'm only looking at that group of animals. I'm only looking at those 18 animals. And so the probability of it being male is going to be 6 out of 18. And that's going to reduce to 1/3, or 0.333. The probability that the pet is a cat, given that it is female. And again, I'm trying to find the probability of a cat. The given information comes second. And so this time, I'm not looking at all the cats, I'm just looking at all the female animals. And I know there's 28 of them. I want to know the percentage that are cats. So that's going to be 12 out of 28. And that reduces, I believe, to 0.429. And the last one, the probability that the pet is female, given that it is a dog. And again, I'm trying to find the probability of it being a female. The given information comes second. And in here, I'm looking now at just the dogs. and I've got 24 dogs, and I'm looking at the percentage that are female. So that's going to be 16 out of 24. And that's going to reduce to 2/3, or 0.667. And so I think in this problem, because you're categorizing the animals along two different variables, gender and the type of animal, a two-way table is going to be a little bit easier to understand in this case. Number 3, there's really no context here. You're just told that the probability of event A is 25% and the probability of event B is 10%. And we want to know the probability of A union B. And remember, A union B is just the probability of A or B. And the probability of A or B, we know, is the probability of A plus the probability of B minus the probability of both. Well, if the two events are mutually exclusive, that means that there is no overlap. That means that the probability of A and B, if there's no overlap, there's no way that the two events could occur at the same time, so the probability is just 0. And so I'm just going to cancel that out. So I'm just trying to find then the probability of A plus the probability of B, 0.25 plus 0.1, that gives me 35%. And if the two events are independent, I'm still looking at the same rule here. The probability of A or B is going to be the probability of A plus the probability of B minus the probability of both. But if they're independent, the probability of A and B, then is equal to the probability of A times the probability of B. So if I'm trying to find the probability of A or B, I'm going to take the probability of A plus the probability of B minus the probability of both. But since they're independent, then I can multiply the two probabilities together. Now, you can't always do this. This is only when the two events are independent. If they're not independent and not mutually exclusive, then you'll have to be given some form of information to help you find the probability of both. And when you multiply this all out, you should end up with 0.325. All right. In number 4, you're actually given a Venn diagram. You're given a two-way table, It says the table below shows the political affiliation of American voters and their positions on the death penalty. So again, we're using a two-way table because we're categorizing voters in two different ways. Either they're for or against the death penalty, and they're either Republican, Democrat, or some other party affiliation. And so if we're asked what is the probability of choosing a random voter, or randomly choosing a voter who favors the death penalty, I'm looking for the probability of favors. Okay, this is just a general marginal probability. I'm not restricting it in any way. I simply need to find the total of the probability who favors, because it means that they could be Republican in favor, or Democrat in favor, or other in favor. And since it's an or statement, I can add all those probabilities together. And I believe that these all add up to, let's see, carry the 1, 3, 62%. If I wanted to find the probability that a Republican favors the death penalty, I'm not given anything in advance. I'm just looking for them being Republican and favoring the death penalty. This is something that I would say people would get confused with the wording. So if it said something like the probability of selecting, I'm trying to say it in the right way, of if you know that the person is a Republican and you want to know the probability of them favoring the death penalty, then it becomes a conditional probability. But in this case, I don't know anything ahead of time. It's just a Republican who favors the death penalty. So they're both Republican and favor. So I haven't restricted this at all. So I'm looking basically at this group of individuals right here, that 26%. A Republican who the probability of a voter who favors the death penalty is a Democrat. So if we know this, if we've selected someone who favors the death penalty, now that becomes known information. If I also want to know the probability that that person who favors the death penalty is a Democrat, this now becomes a condition. I'm trying to find the probability that they're a Democrat when I know that they favor the death penalty. And so if I look at it this way, finding the probability is a little bit easier because I'm only looking at the 62% who favor the death penalty. And I'm looking for the proportion out of that that are Democrats. And so that's going to be 0.12 out of 0.62. And that, I think, is 19.4%. So there's a very slight difference in the way questions B and C are worded. So make sure that you note that difference so that you can tell, like, when something is given to you ahead of time, when something represents a condition. And again, we're looking just at the people who favor the death penalty and looking for the proportion that are Democrat, whereas in Part B, we're just looking for a Republican who favors the death penalty. We're looking for both at the same time. Okay. Number 5 says 20% of cars that are inspected have a faulty pollution control system. The cost of repairing a pollution control system exceeds $100 about 40% of the time. When a driver takes her car in for inspection, what's the probability that she will end up paying more than $100 to repair the pollution control system? So in this case, I'm looking at, first of all, does she have a faulty pollution control system, and will the cost of repairing it exceed $100? So this is going to be a situation where I'm given sort of a sequence of events. And in this case, it's going to make more sense to draw a tree diagram, because either she has a faulty system or she doesn't. And then if she takes it in to get repaired, either it's going to cost more than $100 or it's not. So drawing a tree diagram is going to make a little bit more sense here. So she either has a faulty system or it's not faulty. And we know that 20% have a faulty pollution system. That means that 80% don't. So then she takes it in to get it repaired. It's either the cost of the repairs is either going to exceed $100 or it's not. Oops, let me fix that. All right, and so then I want to put the probabilities in here. So we know that the cost of repairing a pollution control system exceeds $100 about 40% of the time. So if it's faulty, I know that 40% of the time it's going to exceed $100, 60% of the time it won't. If it's not faulty, then the probability of the cost of repairs exceeding $100 is 0. Because if it's not faulty, there's nothing to fix. And so that means 100% of the time the cost of repairs will not exceed $100. All right, so basically we want to know when a driver takes her car in for inspection, what's the probability that she will end up paying more than $100 to repair the pollution control system? So I am simply trying to find the probability that the repair is going to exceed $100. And there's 2 paths that we can take. 1, 2. And if you've constructed the tree diagram, then it makes it really easy to simply multiply across the branches and then add the branches together. Because she could have a faulty system and exceed, or it may not be faulty and exceed. So we'll find that the bottom, or the second alternative, doesn't really ever occur, but the math still works out. So that means we could have 0.2 times 0.4 plus 0.8 times 0, which is just going to end up being 8% of the time. And again, you want to make sure that you are showing the probability statement and showing all of the numbers that you added to come up with that 8%. If you did this problem differently, you just need to make sure you show your work. Okay. In number 6, it says the soccer team shirts have arrived in a big box, and people just start grabbing them, looking for the right size. The box contains 4 medium, 10 large, 6 extra large. You want a medium for you and one for your friend. Find the probability of each. Well, in order to find any probabilities, I need to kind of know how many shirts are in the box. And it looks like if I add the 4 medium, 10 large, and 6 extra large, that's going to add up to 20 shirts. Okay. So the first 2 I grab are the wrong size. So basically, if I'm looking for 2 mediums, that means I got a not medium and another not medium. Now in this case, if you think about it, I'm not putting the shirts back. I think they're just like grabbing the shirts, looking for the right sides. We're not putting them back or reshuffling. So we can't assume independence here. So in each case, I've got to think about the number of shirts that are left in the box as I start grabbing. So the probability of me not picking a medium, well, if there are 4 medium shirts in a box of 20, that means that 16 of those 20 are not mediums. So that would be the probability on my first draw. So that means if I dig in the box again, and I'm again picking out a shirt that is not a medium, since I've already picked out a shirt that is not a medium, that means there are 15 not mediums left. And instead of having 20 shirts left in the box, I only have 19 because I already removed one. And so if I multiply those together, we get 0.632. And again, in a problem like this, you want to make sure that you show me these 2 fractions. Because if you've rounded differently and I can't figure out how you did it, I can't give you any partial credit here. Letter B says, what's the probability that the first medium you find is the third one you check? So that means we had the probability of not medium and not medium, and then we got a medium. So I've picked 2 shirts that were not mediums, and then I got a medium. So it's going to start off the same way. The first shirt wasn't a medium. There's 16 out of 20. I don't put that shirt back, but there are 15 not mediums left in a box with 19 shirts in it now. But if the next one I take is a medium, remember there are still 4 medium shirts in the box. But if I'm thinking about all of the shirts in the box, there's only 18 left now. And if I multiply them all together, we've got 0.14. If I want to find the probability that the first 4 shirts are all extra large, so extra large and extra large and extra large and extra large. Again, we're not putting them back, so we don't have independence. There are 6 extra large shirts in the box out of 20. That's going to be my first probability, 6 out of 20. I don't put them back, so that means that there are 5 extra larges left in a box now that has 19 shirts. If I draw another extra large, that means there's 4 left out of 18. And finally, 3 left out of 17 if the first 4 are all extra large. The chance of that happening would be 0.003. Okay, and that's how you would do number 6. Number 7, we know that 56% of all American workers have a workplace retirement plan. 68% have a health insurance, and 49% have both. If we select a worker at random, what's the probability he has health insurance if he has a retirement plan? In this situation, you could do a Venn diagram since I'm looking at 2 very similar events. We've got retirement plan and insurance. It's possible that they have both. So if you want to construct a Venn diagram, you certainly can do that. We can also just work with our probability rules. But what we'll want to do is list the information that we're given. We know the probability of a retirement plan is 0.56. I also know that the probability of insurance is 0.68%, and the probability of both retirement and insurance is 49. And I want to know the probability that the person has health insurance if he has a retirement plan. So if he has a retirement plan, that now becomes my given. I'm dealing with a conditional probability here. What's the probability of having insurance if we know he has a retirement plan? Well, let's think about the rule for this. The rule for conditional probability is simply the probability of both insurance and retirement over the probability of retirement. And those are two probabilities that I'm given in the problem. It's simply going to be 0.49 over the probability of retirement, which is 0.56. And that ends up being 0.875. Now, you could totally draw a Venn diagram here. So if this is my retirement circle and this is my insurance circle, we start with the overlap. We know 49% have both. If I've got 68% have health insurance, I need to do 68 minus 49. So 58, I think that's 19%. And then if I know that 56% have a retirement plan, I need to subtract the overlap there as well. So that'll be 7%. Hopefully I did that math right. And so again, if I want to find the probability that they have insurance, given that they have a retirement plan, so that means that I'm living in this circle right here, and I'm looking for the probability that they have insurance, which is going to be the 49 out of the total, which is 56%. So even if you use a Venn diagram, you're going to get the same answer. In letter B, the probability, let's see, we select a worker at random, it's asking, are having health insurance and a retirement plan independent? So this is one where you kind of have to construct a geometric proof. Like you have to, what we'd want to know is if retirement and having insurance are independent, then the probability of having a retirement and insurance would equal the probability of having a retirement plan times the probability of having insurance. So I want to see if these two things are in fact the same. So I'm given everything I need. The probability of having both a retirement plan and insurance is 0.49. The probability of having a retirement plan is 0.56. And I want to multiply that times the probability of having insurance. And so if I multiply the right-hand side, I believe you get 0.3808. And that is obviously not the same thing as 49%. So since those values are not equal, the events are not independent. Okay. You could also do this with the using the conditional rule. So for example, I could also look very easily, since I just found the probability of having insurance given retirement plan is 87.5%. If the two events were independent, then this number should be the same as the probability of having insurance, because knowledge of the retirement plan shouldn't change the outcome. And since those two probabilities are different, that's another way to conclude that the two events are not independent. If you wanted to show that they are independent, then you'd have to actually show it both ways. But if you're able to show that one of them doesn't work, then you know right away that they're not independent. Okay, number 8, it says Leah is flying from Boston to Denver with a connection in Chicago. The probability that her flight leaves on time is 15%. If the flight is on time, the probability that her luggage will make the connecting flight in Chicago is 95%. But if the first flight is delayed, the probability that the luggage will make it is only 65%. And we want to know the probability that Leah's luggage arrives in Denver with her. So in this case, I'm not looking at overlapping events. I'm looking at a sequence. So either her flight is on time or it's not, and then either her baggage gets there or it doesn't. So let's start with the flight. So her flight is on time or it's delayed. And we know it leaves on time 15% of the time, which is not a very good probability. That means 85% of the time it's delayed. And then either her luggage is going to make it or it won't. Okay, so then if we take a look at the next sentence, it says, if the flight is on time, so I'm looking at this path here. Let's see, if the flight is on time, the probability that her luggage will make the connecting flight in Chicago is 95%. That means 5% of the time it won't. If the first flight is delayed, now I'm on this path, then the probability that the luggage will make it is only 65%. That means 35% of the time it won't make it. And we want to know the probability that the luggage will make it. Actually, let me put this in part A. This is, right, we want to know the probability that Leah's luggage arrives in Denver with her. So the probability that it makes it. There's two ways for this to happen. The flight is on time and the luggage makes it, or the flight is delayed and the luggage makes it. And so remember, I multiply along the branches and then add the branches together. So this is going to be 15% times 95%. Or if she's delayed, we need to consider the 65% of the time that the luggage will still make it there. And this should end up being 0.695. Okay. In part B, it says, suppose you pick up Leah at the Denver airport and her luggage is not there. What is the probability that her first flight was delayed? So the given information now that I know is that her luggage is not there. Her luggage did not make it. What is the probability that her flight was delayed? So that is what I'm trying to find the probability of. Probability of the delay, given that the luggage didn't make it. Okay, and again, since this is not how our tree is set up, we're not looking at whether or not the luggage makes it first. I can't just look at my tree diagram to answer this question. I also have to rely on my probability rules. And since this is a conditional probability, I have to look at the probability of both, that it's delayed and it didn't make it, over the probability that it didn't make it, or that it won't make it. Okay, and so the probability of both delayed and not making it is going to be the 0.85 times 0.35. And then the probability that it doesn't make it, there's two paths that it could take. Her flight could have been on time and it didn't make it, so that would be 0.15 times 0.05. Or it could have been delayed and the luggage didn't make it, so that would be 0.85 times 0.35. Okay, and that I think is 0.975. So most of the time, if her luggage isn't there, it is because her flight was delayed on that first leg. All right, let's go ahead and take a look at number 9. It says a company's records indicates that on any given day, about 1% of their employees will miss work. The company has 150 employees. What's the probability that at least one of the employees misses work? Okay, so remember, anytime you're asked to find the probability of at least one, so we're looking for the probability of at least one, and I'm doing this 1 in 150 misses work. And I think with these, it's helpful to write everything out. The probability that at least 1 in 150 misses work. That is the exact same thing as 1 minus the probability of none in 150 missing work. Okay, so if nobody's missing work, that means they're all present and accounted for. So all 150 are present. So let me rewrite this. Okay, let's also take a look at what we're given. We know that on any given day, about 1% of the employees will miss work. So the probability of missing work is 1%. That means that the probability of not missing work or being present is going to be 0.99. And so now if I kind of fill that in, if I now want to find this probability, all 150 are present, that means the first one is present and the second one is present and the third one and the fourth one and the fifth one. I'm going to have to assume independence here and that there's not some sort of virus going on. But I can go ahead and use my multiplication rule, which would mean that I'd need to take the probability of being present, the first guy, times the second guy's probability of being present, times the third guy, times the fourth, times the fifth. So I'm looking at taking 99% times itself 150 times, or simply raising 0.99 to the 150 power. And then to finish answering the question, I need to find 1 minus that. And that's going to end up giving me 0.7785. So there's almost a 78% chance that at least one person is going to be absent or miss work. Number 10, Dan's Diner employs 3 dishwashers. Al washes 40% of the dishes and breaks only 1% of those he handles. Betty and Chuck each wash 30% of the dishes. Betty breaks about 1% of hers and Chuck breaks 3% of the dishes that he washes. You go to Dan's Diner for supper one night and you hear a dish break. What's the probability that it was Chuck's fault? So in this case, again, I'm looking at a sequence of events. I'm looking at the person who washes the dishes and then whether or not they break the dishes. So because there's 3 different people washing the dishes, I'm going to have, it's going to be better that I do a tree diagram. So we've got Al, we've got Betty, and we've got Chuck. And each one of them is either going to break or not break. Break, not break, break, or not break. Okay, so let me go through and assign the probabilities. I know that Al washes 40% of the dishes and Betty and Chuck each wash 30. If I add them up, that gives me 100%. So there's nobody else that washes dishes. Let's see, Betty breaks about 1% of hers. So that means 99 are safe. I know, let's see, I know that Chuck breaks 3% of the dishes that he washes. So 97% of those are okay. And I missed Al. Al breaks 1% of the ones that he handles. So that means 99 are okay. All right, so you go to Dan's Diner, you hear a dish break. You want to know the probability that it was Chuck's fault. So we're trying to find the probability of Chuck, but we're given that the dish broke. And again, because the order of my tree diagram starts off with the person, not whether or not the dish broke, I have to rely on my rule here. So to find a conditional probability, that's the probability of both over the probability of the given, which in this case is the break. And so if I'm looking for the probability that Chuck broke it, Chuck and break, that means we're looking at 0.3 times 0.03. But then I also have to think about the probability that a dish broke. Well, there's 3 different ways that that could happen. Al could have done it. There's a 40% chance that he was washing the dishes. And if he was washing the dishes, there's a 1% chance that it broke. Or it could have been Betty. There's a 30% chance that she was washing the dishes, and she has a 1% chance of breaking the one she washes. And then we can go ahead and add Chuck again. And if you simplify that fraction, make sure if you're going to do this in one step that you put parentheses around your numerator and denominator. And it should end up being 0.5625. So if you hear a dish break, there's an over 56% chance that it was Chuck's fault. Okay. In the next one, it says 2 symptoms of a common disease are fever, which we're going to denote with the letter F, and rash, which we're going to define with the variable R. A local doctor reports that out of a typical group of 10 people with the disease, 2 will have the fever alone, 3 will have the rash alone, and 1 will have both symptoms. Determine the probability of each. In this situation, we're dealing with a fever and a rash. They're very similar. It's not a sequence of events. It's not like one is happening and then the other is happening. They both could occur at the same time. So in this case, a Venn diagram is going to make the most sense. So we've got fever and we've got rash. But be careful with the information that's given. The local doctor reports that out of a typical group of 10 people, so I know my sample size is 10, 2 are going to have the fever alone. That means that they're not going to have the rash. That means that 2 are going to be in that part of my Venn diagram. 3 will have the rash alone. That means they're not going to have the fever. And 1 will have both symptoms. And so if I add those numbers together, I get 6. That means that there are going to be 4 more that are outside of those 2 circles. So if I want to know the probability of the person having a fever, that's this whole circle. And if you would feel more comfortable just going ahead and changing everything to percents as you go, you can do that. Or you can look at the count and divide by 10 if that's easier. So if I'm looking at the fever, there are 3 people out of 10 that had the fever, and that would be 30%. If you want, you can go ahead and just write these. Since 2 out of 10 is 20%, 1 out of 10 is 10%, you can change them to probabilities in the Venn diagram if that's a little bit easier. The probability of having a rash, I know, is going to be the 0.1 plus 0.3 because it's going to include the people that have both the rash and the fever as well. If I'm looking at fever or rash, that's a union, so I'm looking at everything in this area. So I'm going to be adding 0.2 plus 0.1 plus 0.3, which is 60%. At least one symptom, that is exactly the same as saying the probability of fever or rash. Or if you want to say that's the same thing as 1 minus the probability of neither. And so fever or rash we already determined was 0.6. If I want to look at it as 1 minus the probability of neither, that would be 1 minus 0.4, which is also 0.6. So you can look at it from either perspective. And the probability of neither, we've already figured out, is 40%. But again, it would be 1 minus the probability of fever or rash, which would be 1 minus 0.6, which is 0.4. All right. I believe this problem I took off of your worksheet because it was just a naked problem dealing with the rules. If you want to do this along with me, it'll just give you a little bit of practice with the rules. So you're given the probability of an event R is 0.5, the probability of an event T is 0.3, and you know that R and T are independent. So I'm going to go ahead and do this just because it's here, and if you want to jot this down in the margin, you can. So if I want to find the probability of R and T, and I know they're both independent, then that is just going to boil down to the probability of R times the probability of T. And I'm given both of those probabilities, 0.5 times 0.3 is going to give me 0.15. If I want to do the probability of R or T, if I just use my general addition rule, that's the probability of R plus the probability of T minus the probability of R and T. And so I know the probability of R is 0.5, the probability of T is 0.3, and I just figured out the probability of R and T is 0.15. And that leaves me with 65. The probability of not T, this is a complement rule, so it's going to be 1 minus 0.3, which is 0.7. The probability of R given T is just going to be the probability of R if the 2 events are independent, which is going to be 0.5. And if R and T are independent, it also means that their complements are independent. So this would still be the probability of T complement, which I already found in part C to be 0.7. And then the question is, are the events R and T mutually exclusive? That is, are they disjoint? So because I know, since the probability of R and T is not 0, because remember, if they're mutually exclusive or disjoint, then they're not going to overlap. Then the events are not independent or disjoint. Okay. So in number 12, it says a bag contains 10 equally sized tags numbered 0 to 9. You reach in and without looking, you pick 3 tags without replacement. We want to use simulation to estimate the probability that the sum of the 3 numbers is at least 18. It says to describe the simulation procedure. So if we're going to do this on our calculator or using the table of random digits, what I want to do is generate the digits 0 through 9. Let's go ahead and say that we're going to do this on the random number table. So using a random number table, we're going to observe, let's look at single digits at a time. Using a random number table, look at single digits at a time. Okay, and what I'm going to do is I'm going to look at them and I want to make sure that there are no repeats. So if I get a repeat, I'm going to move on. So look at I guess 3 numbers in a row, ignoring repeats. I guess I'm skipping repeats. Until you have 3 unique numbers. And then we want to determine the sum. If the sum is more, let's see, it says at least 18. So if the sum is at least 18, I'm going to mark a yes. Okay, you could also just write down the sum and then count the number that are over 18, or at least 18 if you want. So that would be how we would do the simulation. So if we're going to use the table below to carry out 10 trials of our simulation, we want to estimate the probability. So my first trial, if I look at these first 3 digits, they're all unique, right? 1, 5, and 6. Now, since they're all unique, I can go ahead and add the total. So 1 plus 5 is 6, 6 plus 6 is going to be 12. That is not equal to 18, so I'm just going to record a no there. That's my trial 1. My next trial, I'm going to look at the next 3 numbers, 8, 9, and 1. They're all unique, and if I add them up, the total is more than 18, so I'm going to go ahead and write a yes. That's my second trial. My third trial, notice I have 4, 2, and then I get another 2. I'm going to ignore that second 2 and move on to the next number 7. Now I have 3 unique numbers, 4, 2, and 7. When I add them together, 6 plus 7 is going to give me 13. That is not over 18, so I'm going to write no. That's my third trial. I'm going to look at my next 3 digits. They are unique, 0, 6, and 5. The total now is 11. That is not 18 or over, so I'm going to write no. 6, 5, and 1, 3 unique numbers. When I add them together, I get 12. That is not 18 or over, so I'm going to write no. I'm now on my 5th trial. My 6th trial is 4, 3, and 7. So when I add them together, I get 14. That is not 18 or more, so I'm going to write no. Then I have 4, 1, 3. That's my next trial. When I add them together, I get 8. Again, that is not more than 18. When I look at my next 3 numbers, they are all unique, so I can add them together. I get 10. That is not more than 18, so I'm going to write no. Let's see, how many trials do I have? 1, 2, 3, 4, 5, 6, 7, 8. I need to do 2 more trials. My next trial, 4, 9, 3, those are all unique. When I add them together, I get 16. That is still not at least 18, so I'm going to write a no. And then in my last trial, I have 6, 7, and 8. And so that is going to be more than 18, so I'm going to write a yes. And so out of my 10 trials, I only had 2 that were more than, or at least 18. So according to my simulation, only 2 out of 10, or 20% of trials, yielded a sum of at least 18. Okay, so the probability, and you could write it like this, the probability of at least 18 would be 0.2, but you want to just indicate that it is an estimate. So, and it's an estimate based on a simulation. This is certainly not the long run. So if I were to do this maybe 2,000 times, I might find that the probability of having a sum of at least 18 is different than 20%. I only did 10 trials, so that's not enough for me to be confident in that result. All right, this is the last problem. It says the probability that a randomly selected person in the United States is left-handed is about 14%. Among the 28 students in Mr. Miller's BC Calculus class, 8 are left-handed. Could this have happened by chance? So in letter A, it says, describe how you would use a random number table to simulate the proportion of left-handers in a class of 28 students. All right, so we know we have a class of 28 students. If they were chosen randomly from a population that has 14% left-handed. So if my probability of finding a left-handed person is 14%, I'm probably going to need to use 2 digits to represent that. So if we look at double digits, and I'm going to let, if I start at 0, 0, then that means I'm going to go to 1, 3. And that would give me 14 values. If you wanted to do 0, 1 to 14, you could do it that way as well. In fact, let me do it that way. So if we let 0, 1 to 14 represent a left-hander, and all others represent a right-handed person, what we would want to do is look at 28 pairs of numbers at a time, because that would represent the 28 students in the class. So look at to represent each student. And then what we'd want to do is count the number of pairs of digits that are between 0, 1, and 14. So, or count the number of left-handed labels. Okay, and that would represent 1 trial. So it says below are the numbers of left-handers in 100 simulated classes of 28 students. So I'm not going to ask you to do the simulation. I'm just going to give you the results of a simulation. So each one of those dots represents the number of left-handed students in a class of 28. So for example, this dot right here means that I looked at 28 pairs of numbers, and in those 28 pairs of numbers, only 4 of them corresponded to a left-handed person. I did this 100 times. So that means we were looking at let's say 2,800 pairs of digits to do this whole simulation. So I want to know, let's say So below are the numbers of left-handers in 100 simulated classes of 28 students, assuming that the students are selected randomly from a population in which 14% of individuals are left-handed. What do these results suggest about the proportion of lefties in Mr. Miller's class? So we need to go back up to his class and look at it. He says there are 8 left-handed students in his classes. So what I want to do is look at the proportion in my simulation that are 8 or more. So the probability of having at least 8 in a group of 28, so we're looking at least 8 students, at least 8 left-handed students in the class. And this happened 4 times out of, we know there were 100 trials. So that's 4% of the time. And so this is where we start kind of getting into that inference question. If you remember the very first activity we did in this unit, we were looking at groups of 7 people buying sodas and the likelihood that at least 3 would win a free soda. When that likelihood, when we do the simulation, when it turns out to be very small, we say that it's really unusual for us to have seen this by chance. And if that's the case, that leads me to conclude that this did not happen by chance alone. So for example, in this case, it is unlikely for there to be at least 8 left-handed students in a class of 28, because that only happens 4% of the time. And we generally draw the line at 5% unless the problem tells you otherwise. When we get into formal inference next semester, we'll actually set different levels. We call them levels of significance. But if you're not told in advance, we usually let 5% be our guideline. So if something occurs less than 5% of the time, then we say this probably didn't happen by chance if this is what I saw. So my conclusion then would be it's very unlikely to see this many left-handed students in a class of 28. We might suspect then that the prevalence of left-handedness may actually be more than 14% if this is what we actually saw. So I'm going to go ahead and write this out so you have it. So it's unlikely to see 8 or more left-handed students in a class of 28 and remember, we can say it's only 4% of the time. We have reason to suspect, or we have reason to conclude, we'll go ahead and keep up with the suspect, that the prevalence of left-handedness is probably greater than 14%. Okay, because if in fact it was 14%, then the likelihood of me seeing 8 or more left-handed students in a class of 28 would only be 4%. And since that's what I got, since that's what I saw, and it's so rare, it makes me suspicious of the claim. And so in this case, that's what I would conclude, that the claim is probably wrong, and there may be, in fact, a higher percentage of students who write with their left hand.